The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right. So today we're going to keep on working on stochastics. And I guess maybe we start, if you guys have questions from the homework set, since I'm sure you're thinking about that a lot right now. Are there any questions? So should I take this to mean that you have it completely under control? That's good. All right. All right, so since we have Monte Carlo integration, Metropolis totally under control, let's talk about time-dependent probability distributions. So in many situations, we'd like to predict what's going to happen in an experiment. And the fundamental equations of that experiment are time-dependent, so we have different things happening at different times. And so we really want to know what ddt of the probability of some observable. Let's get equal something. Let me fix the lights. All right. So we want some equation like this. And then when you actually made your measurement, you'd be sampling from P. So probability of the observables. And so if you made the measurement, you'd have a certain probability that you'd observe something. And you made a different measurement, you'd have some same probability if you made the measurement at this time. So this is going to be probability of the observable depending on the time. And you made the measurements at different times. So let's conceptually think about this. Suppose we had a box and it had a uranium atom in it. It's radioactive and it can decay. So we look in the box, and at time 0, I look in there, and there's the uranium atom sitting there nicely. And I go away for a while, and I come back, and I open the box, and I look again later. And there's some probability that the uranium atom is still there, and there's some probability that it fissioned during the time, and it's gone. Right? Okay, so there must be some kind of equation like this, how the probability that the uranium atom is still there in the box. Right? Is this okay? Yeah? So just for that case, what do we think that probability, how does that probability behave? Any ideas? So uranium has a half-life or something, right? Yeah, you guys heard this before, right? So let's just try to think of how this should scale. Whatever it is, probably should have something to do with the time constant for how fast uranium decays. Yeah? You guys look at me like so blankly. This is not that hard. It's just one uranium atom. It's okay. Yeah. All right. So let's just write a plausible equation. Maybe it's dp dt, where this is the probability that the uranium is in the box. This might be the probability divided by 2. Something like that. Would that be? All right. I guess we need a negative sign maybe. So then the probability, the solution to this would be that the probability that the uranium is still there is going to be equal to some initial probability e to the negative time over tau. Does that look right? Does this look very reasonable? You might have seen this before? Yeah? Maybe you didn't think of it as probability. Maybe you thought about it as number of uraniums in the box. If I had written it as the number of uraniums is equal to the original number of uraniums e to the negative t over tau, you guys would have believed that right away, right? Yeah? Okay. So I guess maybe this is highlighting an issue here, is that we're used to macroscopic thinking. We're used to thinking of things as continuum, right? But if I only have one uranium there, it's either there or it's not there. It's 1 or 0. So the problem with this equation, if you compute this, it computes irrational numbers, fractional numbers, as the number of uraniums. But of course, the number of uraniums is just either it's integers, right? There's one uranium atom, or there's two, or there's three. So this equation is not right. All right, so this is incorrect. So that was what you learned in high school, right? That equation? But that's not right. So this is really the correct equation, that the probability they have some number of uraniums that does something. Well, at least this works for one atom anyway. All right? So that's the equation for 1. So this is probability I have 1 uranium. It's the initial probability that there's 1 uranium in the box, which is basically, in my case, it'll be 1. I know I put 1 in there. Right? And then it just decays. The probability decays. But it doesn't mean the uranium decays. So it means if I do the experiment once, here I have the uranium, the probability of the uranium is a simple exponential decay time. I know I had a uranium atom there when I first put it there, and at later times it's gone away. Right? Because longer and longer times it's more and more likely it would have fissioned. Now, if I actually do this and buy 1 million boxes and put 1 million uranium atoms, 1 in each one, to start with, and then I just keep coming back once in a while and checking, what I'll see is that initially I had, here's the number of uraniums. Initially I had 1 million uranium atoms. And for some time period I still had 1 million. And then something happened and one of them went away. Because one of them fissioned, turned into lead or whatever they turned into. All right? And so now I had 1 million minus 1 uraniums that lived for a while. And then maybe another one went away. And then this time another one went away. And that time it lasted longer. Right? This is what you really expect to observe. Is this okay? And so this is sampling from the probability distribution. Does that make sense? Yeah, so I'm sampling 1 million times because I have 1 million boxes. This is probability distribution for 1 box. And so I'm able to figure this out. Is this okay? Yeah. All right. So we'd like to write equations like this for more complicated systems. But you're still going to have the same confusion, that the probabilities is going to be a continuous variable, and it's going to behave in ways that seem perfectly sensible to you. But then every time you do the experiment, different things will happen in time, because you have something that's a time-varying probability, and each time you sample from the probability distribution, every time you do the experiment, it's like a particular instance of sampling from that probability distribution, and you might get that there's 87 uranium atoms left. You might get that there's 93. And it's not because of your measurement error. It's because the intrinsic system has its own randomness to it, right? You look at one uranium atom. Some uranium atoms live for 1 million years, and some uranium atoms might decay in the next second, right? And you have no idea when they're going to decay. All you know is statistically, on the average, uranium atoms decay with a certain half-life, which is pretty long, right? All right, is this totally obvious? I can't figure out, is this like totally obvious or totally confusing? It's very funny with you guys, your expressions, totally obvious and totally confusing has the same blank expression. Can someone ask a question? Maybe that would help us to have a... This is okay? All right, this is okay. This is okay. All right, so it's totally obvious. Good, hard to tell sometimes. All right, so Joe Scott wrote some brilliant notes trying to explain how to do this for chemical kinetics. Okay, so you should definitely read them. They're posted under the materials general section. Stochastic chemical kinetics. Nice 20-page long thing, something like that. It's definitely worthwhile to read it. He was very nice at writing very clear notes. So I'll try to explain his notes inexpertly in a short period of time. I strongly recommend you read it. So the idea is that the chemical kinetic equations you guys have all used are also incorrect. Right? Just like this is incorrect. Right? Because this is assuming that something that's really a discrete variable is a continuous variable. And we do this all the time, right? We know that material is made of atoms, and so when you measure a mass in a certain volume, there only can be certain discrete values. But we always ignore that, and we always treat mass as a continuous variable, right? So you have some flow, some amount of liquid, and you have some amount of mass, and it could be any number. And we treat d, d m dt, or things like dm dx, d rho dx. We write those down as if everything's perfectly continuous variables. And that's because that in a lot of systems we have so many atoms, and we can't measure that well anyway, that we couldn't tell if we were missing one or two atoms. Whether we end up with an extra half an atom in our equations or not makes no difference, because we're not that precise, right? So we don't worry about it. So we use continuum equations everywhere. But in many cases, what we really should be using are continuous equations for probabilities. And then, as I'm going to show you how you do it for chemical kinetics in a minute. I'd say that this is super fundamental, actually. So quantum mechanics says that everything is wave functions, which is actually like the square root of a probability density. And the real equations are really probability densities. And so that's the real fundamental equations. Really, everything is probabilities. And when you make an experiment, you're just sampling from the probability. And all our continuum equations are like approximations. They're only valid in like the large number of atoms limit. Okay? So just, I know this takes maybe a change of thought, because you're so used to those continuum equations, you start to believe they're really true, right? Right? You've probably used them a lot, and you start to feel like you love those equations. They're your favorite equations. You have a relationship with them. Some of them you might hate, some you love, but at least you have a strong connection with them. And you find out that actually they're not even related to the real equations. The real equations are actually something different. It's be very annoying, but it's true. And when you get to smaller and smaller systems that have fewer and fewer molecules in them, then you get more and more sensitive to the fact that the regular equations are incorrect. And this comes up a lot in small systems. So many of you probably will do research that has to do with biology. In biology, there's cells. Inside cells, there's like subcellular structures. Inside those subcellular structures, there's not very many molecules. And so you often are at the limit where you have like one molecule of a certain type inside this, a mitochondria or something. And that's it. And so you wouldn't expect the continuum equations to work. And in fact, there's a big field many people research doing here called single molecule spectroscopy, where you can measure the motion of one DNA molecule or something like that. And so you really see the individual molecules and the effects of the individuality of the molecules. And this is not only true in biology. For a long time, there's a field called emulsion polymerization. You guys ever hear of this? So like all the paint on the walls here is made by that process, where they polymerize methyl methacrylate. They want to make the little beads of polymers all have as small dispersion as possible to make all the molecules the same. So what they do is they make a colloidal suspension. I'll draw a little picture. So they have a reactor. They make little bubbles of the monomer that are suspended in some solvent. And inside each of these bubbles, because of the way they make them, they're all about the same size. So they all have a lot of bubbles all about the same size. And then they polymerize, and they polymerize each of them, and they polymerize, and basically all the material that's there polymerizes into one molecule. Now, how do they make that happen? Is that they introduce, say, a free radical, and one free radical gets into one of these bubbles, and it can polymerize the whole thing, because the reactions are radical plus monomer gets to a polymer, bigger polymer. Right? So polymer radical size n goes to polymer radical size n plus 1. That's the polymerization reaction. Now, normally, if you did this in the bulk, there'd be a lot of radicals, and some of these guys would react with each other, and the radical would be gone because the two radicals would react, make a new chemical bond, and this process would stop. And so this gives a big dispersion in the size of the polymer chains you get. So to beat this, they do emulsion polymerization, and they make the number of radicals so small that statistically at any time, any of these droplets either has 0 or 1 of radicals in it. And there's not, during the time it does the polymerization, there's not enough time for a second radical to come in. So it's only got one radical. So that one radical is going to eat up every single monomer molecule in the whole thing. And so it's going to make a giant polymer. That's the whole size of the emulsion. If you made the drops too big, you get two radicals in there, you get some of this happening, and then you get a dispersion. So this is emulsion polymerization. All right, so cells have small little volumes. Colloids and emulsions have small little volumes. They all have some of the molecules, the important molecules, are have such low concentrations, the volumes are so small that the concentration times the volume is less than 1 or about 1. So that's for your copies of DNA in you, in your cells. It's the same kind of thing for radicals, free radicals in a polymerization system. And the similar things can happen with like explosions, different kinds of rare events. You might have a very small number of some really important molecule. And then whether or not you have one or not is really important. Okay. All right, so we want to model those kinds of systems. We have to worry about the graininess. So we want to write down what the equation is for dp dt. So first we got to think, what is P? Let's do a case where we have the reaction of A plus B goes to C. Okay, suppose this is the only reaction that can happen in our system. The only molecules we have in our system are A's, B's, and C's. And so our probability distribution, or probability we want to know is how many A's, how many B's, how many C's do we have in our system? Okay? So that's the probability we're interested to know. We could have 5 A's, 2 B's, and 0 C's. We could have 3 A's, 7 B's, 11 C's. Who knows, right? Different numbers like that. If it gets up to be 10 to the 23rd, then there's no point. You don't have to do this because you can just go back to your continuum equations. Right? But if you have 5 or 3 or 2 or 1 or 0, then you really need to worry about the graininess. So you want to write down an equation. So here's the probability of Na, Nb, and C. And it's going to equal to reactions which consume, if I'm in this state that has a certain number of A's, B's, and C's, and I can react away. So we have reactions, for example, I'm in this state, and A plus B could react with each other, and will react away. So I'll have some reaction. I'm going to write it K, but we'll come back to what this really means exactly in a minute. So this is the K for A plus B going to C. And we think that this is going to scale with the number of A's and the number of B's I've got, right? And this depends on the probability that I have A, B, and C. Okay, so if I'm in this state with NAs, NBs, and Cs, that probability is going to go down because the A's and B's can react with each other, right? Now on the other hand, I have plus the same K, and this is going to be Na prime and B prime. If I have some other state that can react so that it makes this state, then I'll get a plus sign because the probability of the state would increase. So for example, if Na prime is equal to Na plus 1, and Nb prime is equal to Nb plus 1, and Nc prime is equal to Nc minus 1, then that state can react by one of these A's and one of these B's combining together to make a C that will get me to this exact state here. Does this make sense? All right? So that's the master equation if I have a system that can only do the irreversible reaction A plus B goes to C. So I can go away because the probability density of this, the probability of this state can reduce because that reaction occurs starting from this state, and the probability of this state can increase because I started from this other state here, the special state here, and that would make the state of interest. All right? And so I have this equation over and over again for every possible value of Na, Nb, and C. Is this okay? Now I have to actually remember for chemical kinetics that whenever you have a forward reaction, you also have the reverse reaction. So there's actually a couple more terms. So now I have another loss term. This is C goes to A plus B. This is going to depend on the number of C's. And that's a P of NA, NB, and C. And then I have another source term. And this is where I start from the state with one more C. Is that okay? So this set of equations is called the kinetic master equation. And this is the equation that describes the real system. So this is the real probability of finding the system with any number of A's, B's, and C's. And I have an equation like this for every different possible number of A's, number of B's, and number of C's. All right? And it's not bad as an equation goes. It's a linear differential equation because it's linear in P's. Right? There's just everything's first power in P. So in general, I can rewrite this as dP dt is equal to some matrix times B. Right? And the matrix entries are these prefactors, things like this, this. These are the different elements in the matrix M. All right? Yeah? So you should go ahead and be able to write any kinetic equation system, rewrite it in this form if you want. It's called the kinetic master equation. All right? Now, if I do an experiment like I talked about with uranium, where I put one uranium atom in there, and all uranium atoms can react to do is fall apart to lead plus neutrons, or whatever the heck they fall apart to. So I can write down there's like one reaction that uranium nuclei do. And so I can write it out, and it'll just be something like this. And this equation will work, for a case where I put one uranium atom there to begin with. I could do a case where I put two uranium atoms in there to begin with. I could write this down. Is that all right? Okay. Now, if I had a case where I had 27 A's, 14 B's, and 33 C's to start with, then you can see that the number of possibilities here might get pretty large. Because I have to consider, well, I could lose one A and lose one B and get one more C. But then I'll have an equation for this term, which will look just like this. But it'll go to ones that have lost two A's and two B's and gained two C's. And then all the way down until I get down to one of the ends to be 0. Right? And so it could be quite a lot of possible equations. Right? So the dimension, the length of the vector P might get really long. Right? So the length of P is something like the max number of A's, max number of B's, max number of C's. All right, so if I have, I consider systems with up to 10 A's, 10 B's, and 10 C's, then this is 1,000. P is a length of approximately 1,000. And it might be less than that because maybe there's some particular states I can't get to. All right, so maybe it's less than 1,000, but something like 1,000. On the other hand, if I allow up to 1,000,000 A's, 1,000,000 B's, and 1,000,000 C's, then I have like 10 to the 18th length of P. So P gets pretty long pretty fast when the number of possible states goes up. Right? Is that all right? So now it's linear though, and it's linear, and this is constant coefficients, and so this is really not and sparse. So this is really, it's not that bad. And in fact, Professor Barton's group has worked on these kind of problems, and he has a solver that can work with p at dimension up to 200 million. So if you can keep the number of states 200 million or less, you can actually solve this exactly. Now solving this exactly is really good, because then you actually have the exact probability of any observable measurement that you would possibly make at any time, all computed. Okay? So that's really great. But as I just pointed out, if I make these numbers like 10 to the 6, 10 to the 6, and 10 to the 6, this is like 10 to the 18th. That's a lot bigger than 200 million. And so Professor Barton's numerical methods are going to poop out at some point and not going to work for you anymore. So there's a limited number of problems you can do. So if your problem is small enough, you just solve this. For really small ones, you can just solve this with OD45 or OD15S. But because it's linear, there's special solution methods. I don't know if you remember solutions of linear equations like this. You can relate them to the eigenvectors and eigenvalues of M. And so you can do, that's one way to do it. And then there's special methods you can do, talk to Professor Barton. If it's sparse and certain kinds of properties, you can make this really, you can make quite large systems, up to 10 to the 8th kind of size. If you get a system with more than 10 to the 8th possible states, that means more than 10 to the 8th possible things could be observed. Or could, the result of the experiment could be have more than 10 to the 8th possibilities. Then this is, you're not going to be able to solve it this way. And so then we're going to have to use a stochastic solution method to try to figure to do this. So we're going to try to sample from P of t. So I guess I should comment. Again, I wrote this way, but this thing, P is definitely depends on time. So you'll have a different P for every time. So, all right, yeah. Yeah, maybe I do better. I can substitute in here. Is that all right?
So you transfer from the neighbor's state.
Yeah. There's a key idea is that chemical kinetics only does one step at a time. So if you have a reaction like this, at any instant, the probability that two reactions will be happening exactly at the same instant is negligible. So at any instant, you're only changing the numbers of the atoms by one unit. Yeah. Maybe I got this backwards. Na plus 1 plus 1 minus 1. Minus 1 minus 1 plus 1. I think this is right. So this is for the forward reaction that always reduces the number of A's and B's. And this is the reverse reaction that always increases them. And so I think you generally get like this. You always get, for any reaction, you'll have 4 terms. So the forward and reverse, starting from the initial state, and the forward and reverse that make your state. All right. And then if you have more reactions, you have a system, you have a lot more reactions. Maybe you have C can just decompose into B's or something, different reactions. Then you'd have a sum like this with terms like this from every reaction. And you go through all your list of all your reactions. All right. I guess there's one funny thing I should point out to you about this, which is very important for this emulsion polymerization case, is that if you have a reaction of the type A plus A goes to, I don't know, B. Okay? That might be a reaction you could have. That when I write down the equation, if I only have one A in my sample, this probability of this happening is 0, right? Because I need 2 A's for this to happen. So really the equation for this case is Na times Na minus 1. So it's K, A plus A goes to B, times Na minus 1. All right? And this is crucial for like the emulsion polymerization case, because the fact that don't have a second one is really important. All right? Otherwise, I always miscompute that this radical could react with itself and terminate itself, which is not true. Is that all right? I commented that these Ks are a little bit odd. So if you remember, if you have a K for a unimolecular reaction, like C goes to A plus B, what units would it have? What are the units for in regular kinetics? Right, inverse seconds, right? So you would normally say this thing has units of inverse seconds. And that works fine here, right? Because I have dp dt, and it's inverse seconds times p, so it's fine. However, this guy, to make the units work out, still has to also be inverse seconds. But that's not normally what you would have for a bimolecular reaction, right? And the other thing to watch out for here is that I have n's, but normally you would write them with concentrations, right? You'd have the you would write something like K times the concentration of C. It's the normal way you write your equations, the rate equations. But this is not the same, right? This is n. This is unitless. Now, it turns out, in this case, actually, you can use exactly the same K and it works. But for the bimolecular case, it definitely does not work. The units are wrong. And also, this concentration thing implies that we think the rate really has, suppose we have Ka, Kb. I could rewrite this as K times Na over the volume, Nb over the volume. Is that all right? Actually, one thing I should warn you about, that usually when I write this, I write moles per liter. So I factor the 10 to the 23rd between this and this, because these n's have got to be the individual molecules for this to work. So watch out. First of all, there's a 10 to the 23rd somewhere in here, right? Avogadro's number. And then this is how we would normally write it, but this K has the wrong units for us here. And so this guy here is the normal K divided by the volume. I think that's right. Maybe it's the other way around. No. This is normal K times the volume. That's right. So normally we would write the units K normal kinetics, macro, K for A plus B reactions. The units are centimeters cubed per mole second. But we want them to be units of the new K has got to be units of per second. And so the new K is equal to the old K, new, old, times the volume. Is that right? No, divide by the volume. I was right the first time. This is volume. Yeah. Thank you. Centimeters cubed. Centimeters cubed. Yeah. Right. Cancel it out. Good for a second. So this is K per volume. Normal K divided by that. Correct. And you may wonder, well, how come it's only volume to the first power before I had volume to the second power in the denominator? And it's because I'm using n's up in the numerator. And it's just like here, I'm using n's instead of n over v. So I've sort of multiplied through by v everywhere. That's one way to look at it. All right? No questions yet? Yeah. Yeah, so I need the 10 to the 23rd as well. So there's got to be an Avogadro's number. And you'll have to help me where the Avogadro's number goes. But it's got to be in there somewhere to get from moles to molecules. So the numbers are a lot different. Yeah. Is this okay? In this factor, this n minus 1 thing, again, when these are macroscopic numbers like 10 to the 23rd, this makes no difference, right? That's minus 1. So we can fit our data ignoring the 1, it's 1, perfectly well, the law of mass action, it works fine. So you never notice this unless you get down to where n is very small. But this is actually the truth. This is really what the correct equation is. All right? Okay, so now we have the true equations for predicting how the probability distribution evolves in a reacting system. By the way, you can add transport in as well if you want. So if you have control volumes and you know what formulas for the rate at which stuff is transported in and out of the control volume, you can add those terms in as well, and they'll affect the probability distribution. Okay, no problem. You should be able to do the same conversion. So just we converted the reaction equations. You can write a similar thing. Once you can write the macroscopic transport equation, you can figure out how you would reduce it down to a time constant for transport that would work for this microscopic version of the equations. So transport and reaction, you can write the whole thing down as the master equation. That's the real solution, the real equation. And the problem is that the real equation oftentimes is too big because P scales up so rapidly with the number of possible states. So then we have to figure out how we're going to solve it. And the way to solve it is called Kinetic Monte Carlo. And this method was invented by a guy named Gillespie. And the journal paper is posted. And this is just like with Metropolis Monte Carlo that you just did. We're trying to find a way to sample from the true probability density without ever computing the true probability density. Right? So in the Monte Carlo integration you're doing for homework, you're sampling from the true Boltzmann probability density, but you never actually explicitly write down what that P is. Right? And so we're going to do the same thing here. Is we're going to, from the differential equations, from this differential equation system here, we're going to try to somehow never ever solve this directly, but instead just sample from the solution, P, which depends on time. All right? And the way it's done is really to try to follow individual trajectories of what could have happened. Okay? So at any time step, we have some number of A's, B's, and C's. And we're going to say, well, in the next time period, some small time period, what can happen? And we're going to make the time period so small that the only thing that can happen is nothing happens, and A, B, and C stay the same, or one event happens, which will change like one of the numbers, the A's, B's, and C's, by, say, one reaction amount. Okay? And then after we accomplish that, now we have a new state, A, B, and C with some new values, and we'll do the same thing again. And we just repeat that over and over. So it's very brute force. You're just doing like what a single system would do. So for example, for the uranium atom case, we have one uranium atom in there. We wait for some time period, say 20 minutes. We compute the probability that the uranium would have decayed in the last 20 minutes. It's pretty small. And then we'll say, okay, now we'll draw a random number. If the random number is less than that probability, then we think that the uranium atom is still there. And the random number is bigger than that probability, then the uranium atom is gone. If it's still there, then we'll do it again. And we'll just keep doing that over and over again. And we'll sample what could happen. The uranium atom could live for 3 years and 14 minutes and then disappear. And that would be one example. And then we go back and we do it again from a different trajectory. And we do it over and over and over again. And we do it over and over again. Those trajectories are sampling from what could happen with the right probability density. Does this make sense? So the way Gillespie says to do it is figure out the expected time until something would happen. And we'll call this time tau. Okay? And we'll pull. Actually, let's not use tau because I'll try to be consistent with Joe's notation. He calls this thing 1 over A. Okay. So A is like the expected rate per second, and 1 over A is the expected time until something would happen. And then we'll draw a random number. R, he calls it R1. So we just call the rand function. It gives me a number between 0 and 1. And I'll say that my time step, delta t, which Joe calls tau, is 1 over A, the logarithm of 1 over R1. And I think there should be a negative sign. No, 1 over R is positive. That's right, positive. All right, so I choose a random number, suppose it's a half. Then this fraction is 2. 1 over a half is 2. Logarithm of 2 is some number bigger than 1. And I pull that and I get some, actually some number less than 1. Logarithm of 2. Anyway, some positive number. Multiply it by the expected time until something happens. And that's the time in this particular simulation when the next thing happened. And then I repeat this again and again and again. And I get a period of time intervals between when something happened. Now, every time something happened, I have to figure, well, what happened? So if I look at my plot back here when I had the uranium, I waited along in this particular case, here's my tau, I'll call this tau 1. The time that it took for the first thing to happen. And then, well, what can happen? The only thing that can happen with my single uranium atom case is it decayed. So it went away. All right, and then I did the random number thing again, and I draw, and I get a different number this time. How long until something happened? Now notice, and maybe it's not so obvious, that the time until something happens changes as you run. So for example, if I start out with 100 uranium atoms in 100 little boxes, and I'm watching them, after I've run this for a long time, I only have 50 uranium atoms left. And that means that the average time period until something happens will be slower because I don't have as many. The more I have, the more rapidly something will happen. Does that make sense? So I have to compute this A thing at each iteration. So I compute the time until something happens. Then I'm going to compute what happened. I'll tell you about that in a second. In the uranium case, the only thing that can happen is one of the uranium is decayed. So I took that away. Now I have to compute A again. So A is the sum of all the things that can happen. So in my case where I have 100 uranium atoms, I have 100 different boxes. In each one of them, there's a rate at which the uranium atom's probability is decaying. It's like 1 over the normal half-life uranium, something like that. And I add them up. So A is the sum of the rates. Of everything that can happen. So we just list out all the different things that can happen. So in the case, suppose I have two boxes, 2 uranium atoms. I can have decay of uranium atom number 1 or uranium atom number 2. So I have this thing would be equal to 2 uranium atoms. A is equal to 1 over tau normal for a uranium atom plus 1 over tau normal, because they're both normal uranium atoms. So it's equal to 2 over tau. And so 1 over A is half of the normal lifetime. And that's when I would expect that something would happen by then. Okay? One of them would probably decay. So that would be the A value I would use. Here, draw my random number, get my tau until something probably happened, then figure out what happens. Now, in the kinetics case, several different things can happen, right? I wrote down, if I'm in state NA, and B, and C, the state can change by two different ways. I can move out of that state this way or this way, right? Two different reactions can happen, forward or reverse reaction, and they would both take me out of the state. So those are two different things that happen. And so I have to add those rates. So I would add this number and this number, and they would be the two things that could happen. And that would give me the A value. Now, I figured out something happened, but now I'm not doing uranium. Now I'm doing, say, number of A's. And I figured something had happened, and now I have to figure what happened. And the number of A's could have gone up or gone down. Because if it was a forward reaction, the number of A's went down. If it was a reverse reaction, the number of A's went up. So I have to decide which way is going to happen. So I could have either the number of A's went down or the number of A's went up. Those are the two possibilities. I have to figure out which one happened. I have to draw another random number to figure out which one probably happened. So I'll list out the list of all the things that can happen with their rates. And one of them, say, is twice as big as the other. So then it'll be twice as likely to happen. So I have to choose a random number and use that to choose the next one. So here we go. So first I figured out, this is actually what we did first. I figured out what my rates are. Second thing is I figured out the time until something happened. Third thing is I'm going to figure out what happened. And what I do is I say, I draw a random number, call it R2. And if there's only two possibilities, like in this case, then I can say if R2 is less than the rate of process 1 divided by the sum of the rates, which is the same as the A, right? So this is, if this is true, then process 1 happened. On the other hand, if the random number I chose is larger than this ratio, then I'll say process 2 happened. And that's how I decide whether the number of A's went up or went down. And then I would recompute the A depending on what happened. Suppose I do this and I found out that the number of A's went up because by drawing the random number. Then I'll go and I'll recompute the A. Now the rates will all be different because NA is bigger, so the rate of the NA reaction is faster. So I recompute it. I redraw a number here. I get some different time. Tau 2 is not the same as tau 1. And then something happened here. I do the same process here to figure out what happened. Maybe this time A reacted away and it went back down. All right. And then I do it again. And this time I draw a longer time, tau 3. And I do what happened, and maybe this time again something reacted away and it went down. And on and on and on. And after my computer's done doing that for a while, I get to a long enough time, I say, okay, I'm done. Oh, I'm not really done. I have to go back and start again and run another simulation to run through all the possibilities. And I want to save all these results of all these simulations because these guys are samples from the probability distribution. And if I build histograms and stuff from those guys, I can figure out what really is going to happen. All right, so it's a way to represent the P. Questions? All right, perfectly clear? All right. So what's nice about this is actually, it's not that hard. Once you do this once, it's not hard to do it, and you can do it for any problem at all. And so it's like, often cases people do this even for cases where you actually could solve, you might be able to solve this equation, A lot of times people won't do it. They'll do this instead, just because it's so easy. So although maybe it looks hard to you right now, it's only like a 3-step thing, and you just do it over and over again. You're not doing it. The computer's doing it. No big deal. And so this one, you have to like look at the sparsity pattern of your M, and it's complicated stuff. So this is actually done extremely commonly. All right. See you on Friday.